Okay, so in this lecture, we're going to discuss the efficiency of training a language model. So how do you train a language model efficiently? Okay, so it's language model training efficiency. Okay, and so note that this applies to all kinds of models, all kinds of sequence models. So for example, CNNs, RNNs, and transformers. So it doesn't matter which class you are taking, this lecture still applies. Because it doesn't have to do with the model architecture, it has to do with how you train the model, how you pass the data in. Okay, so for that reason, we can just think of our model as a box. So we know that for all of these models, we have learned that there are different modes of operation. Okay, so for example, there's so these are the inputs. So we have many inputs, and these are the outputs. And so, for example, we might have one output, one, or we could have something like this, where it's many inputs and many outputs. Okay, so this is many to many. Okay, and so we know that in terms of the theory, what we would like to do is we want to take some string of letters, so that's x0, x1, up to x of, let's say, t, and we would like to predict x of t plus 1. Or another way to think of it is we're estimating this probability distribution, p of x of t plus 1, given x of t down to x of 0. Okay? So that's conceptually what we're trying to do. And so you can see that with this setup, it's pretty clear that we have many inputs and one output. So you might think that this is the model we should use. But in fact, this is inefficient. So we could do something like this. So where we have, actually, you know what? We'll talk about the efficiency later on. Instead, I'll continue talking about how it works, and then we'll talk about why it's better. Okay, so my goal in this lecture is to convince you that, in fact, we should use many to many, and that's actually better. Okay, so how does that even work? So let's say, for example, we have an RNN. This is easy to visualize. So an unrolled RNN looks like this. So we have H0 coming in here, and we have X0. This is H1. We have X1, and so on and so forth, up to H of t minus 1, and this outputs H of t, and this outputs, or takes in as input, X of t. Again, at the top, we can have a dense layer or an ANN. So we draw that like that, and then this will output y1, y1, call it y1 hat, and then y2 hat. Okay, and this outputs to dense layer, and this is y of t plus 1 hat. Now the indices might be inconsistent to what I've done elsewhere in the course, but that's not a huge issue. It doesn't matter what you call them, just the architecture matters. Okay, so you can see that this is the most full RNN we can make, the one where we pay attention to all of the t plus 1 outputs. And my proposition is that we should actually pay attention to all of these. Okay? So as an example, let's say we have a simple sentence, such as, I like cheese. Okay, so I like cheese. Okay, and so what we're going to do is, for the input sentence, what we're going to do is we're going to add a token to the front. So we'll call it a start token. And then we'll go to I like cheese. And these will be the inputs into the model. And the output that we're trying to match to, the target, is, so here's I. And here's like. And here's cheese. Okay, and you might be wondering what goes here. And again, we add another token, which is the end token. Okay, so you can see we've added one extra token, where for the inputs we added at the front, we call it the start token. And for the targets, we added at the end, which is the end token. Okay, so what we're teaching the model to do is when the first token, when the input token is the start token, we want to predict the first word of a sentence, which is that. And then when we have start I, we're trying to predict like. When we have start I like, we're trying to predict cheese. And then when we have start I like cheese, we want to predict that it's the end of a sentence. Okay, so hopefully that makes sense. And the reason that this works is because these are actually the same weights. Right? It's an R and N, and we've just unrolled it. Okay, so it's the same weights for every time step. And so mathematically, it would be equivalent to doing the one output version. It's just that this is faster. Okay, and so how is this faster? So because we have 4 targets now, this means that we effectively have 4 samples. Okay, so let's look at the other perspective where we try to do this with the one output case, the many to one RNN. Okay, so what that would look like is we have one sample that just says start, and we want to predict the target I. So this is the input, and this is the target. Okay, so that's one sentence, or one sample. And then we have start I, and we want to predict like. And then we have start I like, and we want to predict cheese. And then we have start I like cheese, and we want to predict end. Okay, so in general, for any sentence that we have where it's say x1, x2, up to xt, we need to make all these different samples. Okay, so we have start, I'll just do it like that, so save time. And we want to predict x1, and then we have start x1, want to predict x2, or yeah, x2. And then we have start x1, x2, we want to predict x3, and so on and so forth. So you can see that with this method, what we have to do is, for a sentence of length t, we actually have to make t plus 1 input samples, which will take up a lot of space and a lot of extra time. Versus if we use the many-to-many method, that one sentence only has to go through the model one time. And obviously for transformers, which are much bigger models, you don't want to increase your runtime that much because they're big and slow. So it's much better to be able to process each sentence one at a time simultaneously without having to break it up into different time steps. Okay, and so as an exercise, you can try to convince yourself that this is actually equivalent. So both ways are equivalent due to the weights being the same at each time step. Okay, so just as a simple example, you can use a simple RNN, which is much simpler mathematical form. So we would have, so our h of 1 would be, let's see, sigma of w, let's call it, and then transpose x1 plus b. Okay, and then we have, oh, and then plus, right. So we'll call it w input plus w hidden transpose h0 plus b. And then we'll say y hat 1 is equal to, again, some activation function. We'll just call it sigma. And then we have w output transpose h1 plus, let's call it c. Okay. And then we have h2, which would be sigma wi transpose x2 plus wh transpose h1 plus b, and then y hat 2 equals sigma of w0 transpose h2 plus c, and so on and so forth. So you should convince yourself that these same calculations take place no matter which architecture you use. And I realize I may have just changed how we represented the x's. So here I started from x1, and up there I started from x0. So unfortunately it's a little inconsistent, but hopefully you still get the idea. Okay, so it's, to summarize, many to many process T samples at once versus many to one process T plus 1 samples individually. Okay, and another thing to think about is that when you process these samples, it's actually not just a linear increase. So for these T samples, when you process them, it's suppose that the model takes order T time to process. Let's just say there's T steps. Okay, so it's once. And so for many to many, there's T computations. Okay, but for many to one, so the first time we do it, there will be one computation. So just imagine how many times we go through each of these blocks. Okay, so for example, the first time, it's just this. So we go through the block once. Okay, so that's why when we have the full sentence of size T, we go through T times. But for many to one, so we go through once. For the second time, we go through twice. For the third time, we go through 3 times, and so on and so forth, up to T. So the last time we go, we still have to do it T times. Okay? And so the total time is 1 plus 2 plus 3 plus T. Okay? And I think they do this example in high school maybe, is what is the formula for this? I believe it's something like T times T plus 1 over 2. Okay, but this is O of t squared, meaning it's quadratic. Okay? And so for a model like transformers, which are already quadratic in t, it becomes even worse.